Hi, let's continue, shall we, about some cardiovascular physiology. In this section, we are going to learn about compliance, which, as we'll learn at the end, is something called vascular resistance. So, when we're looking at blood pressure determinants, because this is where we've started, and instead of starting on the left, because we're not there yet, we're going to start here on the right. The blood pressure is determined by a couple of physical factors. Number one, the volume of the blood. So generally we're talking about in somebody who is not being given volume into their body that significantly changes their blood volume, or who is losing at that time. And so we're going to pretend that that's not changing right now. Now, obviously in the case of an accident that would change, and that affects all these other factors. And then they would be changed again once you started giving intravenous fluids to that person. But let's just assume that stays the same. So then the factor that's physical that's going to affect blood pressure has to do with arterial compliance. So what is that? Basically, elasticity. So it's the ability of the walls of that blood vessel to do two things: expand, and then when it doesn't need to be bigger because there's a decrease in blood volume, to contract passively. So this does two things. So at the top, here on the left, we have an elastic artery showing what happens during ventricular systole. This ventricular systole here. And we have this big bolus of blood that goes, for instance, into the aorta. Then the aorta, because it's an elastic artery, it has great elasticity, and it will expand so that the systolic blood pressure doesn't skyrocket. This also keeps the pulse pressure in a normal range as well. And then once the ventricle is finished with systole and is in diastole, if we kept that blood vessel big, well, then there wouldn't be any pressure on the blood vessel walls to have blood continue flowing. So during diastole, the elastic blood vessel has to narrow its lumen so that we have an increase of flow during diastole. Now compare that normal elastic artery to one that is stiff, for instance, from atherosclerosis. It can neither expand to give us compliance during systole, nor contract to give us compliance during diastole. And so we can tell that because systolic blood pressures and pulse pressures are going to be artificially high compared to ventricular pressures, and diastolic flow is going to be lower. So reviewing elastic arteries, remember here in the tunica media, we have elastin fibers throughout it. And so this allows the stretching and the recoil, giving low resistance to large volumes. Okay. And because of this, the elastic artery then kind of acts as a temporary pressure reservoir, because during diastole, the elastic arteries contract down, generating pressure, which propels blood distally. So that's why it's important to not only have the distensibility, but also the contractility back towards the normal lumen size. Now, in contrast to elastic arteries, as you recall, muscular arteries had lots of layers of smooth muscle in the tunica media, up to 20 to 40 layers, but at least over 6. And because of that, we had 2 discrete elastic lamina. And so here's a blood vessel that is in a muscular artery in the middle, which is normal. And then all those layers of blood, smooth muscle, can contract, giving us a vasoconstricted blood vessel, or on the left, they could be actively vasodilating, giving us a larger lumen. So our muscular arteries are very active in this vasoconstrictive vasodilation thing. So there's a good influence here from nitric oxide. I wrote nitrous oxide, please change that to nitric oxide, as well as some sympathetic stimulation, and as well as effects of other chemical mediators, for instance, causing vasospasm after injury. And let's also review our arterials. So these don't have any elastic tissue, but they just have either wisps as shown in this upper right one, just like one little smooth muscle fiber, or they could have 2 or 3 layers of smooth muscle fiber. So they do have some sympathetic nervous system innervation. So they contribute to resistance because they can vasoconstrict. Okay, so sympathetic nervous system, hormones, local chemicals. And so what these are doing, remember the arterials, what's feeding into the capillary bed. So these control the minute by minute flow into a capillary bed. And so the size of these arterials actually do have a direct impact on the blood pressure, because if we vasoconstrict those precapillary sphincters, then blood's going through the medarterial into thoroughfare channel rather than more blood going all the way through the capillary. And so by preventing all the blood going through the capillary, that's keeping more blood in the major blood vessels, thereby artificially elevating the blood pressure and actually decreasing the blood flow to actual tissue. So it's kind of a win-lose situation, but for certain organs, it's much more important. So looking at an overview, starting here on the left, we have the left ventricle, and in systole, it generates a significant amount of pressure, and then diastole, it completely relaxes and the pressure goes down to 0. Our large arteries are elastic arteries, and because of their compliance, their distensibility, they maintain the upper level of the blood pressure, hopefully, theoretically, the same level as it was when it's leaving the left ventricle. And then because of the fact that they have elasticity and contract down, during diastole, their blood pressure levels do not go all the way down to 0. Now, as we move through the muscular arteries into the arterioles, what we'll notice is that the systolic blood pressure is progressively falling, as well as the diastolic blood pressure. So these are our resistance vessels. Which brings us to the term systemic vascular resistance. This is how we measure compliance. So you need to go back and look at what affects this. Well, a change in viscosity. For us, we're going to put that by the wayside because we're not going to be changing viscosity in any of our problems. This is an introductory class. A change in the vessel length. Once again, that we're going to put that aside in our calculations because we're not going to be changing vessel lengths. So the only factor that is affecting us is the vessel radius. So our compliance, whether we're vasoconstricted or vasodilated. The major influence for systemic vascular resistance is the radius of the vessel. And so systemic vascular resistance also has some synonyms. It's also known as peripheral vascular resistance because the heart is central and this is all peripheral. And sometimes it's also known as total peripheral resistance. So that is it for this section. I want to thank you. I think by now you figured out we're covering different little topics, and we're going to have, half dozen or so of those before we start trying to combine them together to hit bigger concepts. So thank you again for working at this and trying to understand, and definitely for doing any of the little questions that I posit to you just to make sure you understand.